Let's today implement the factorial function in the pure lambda calculus. So just lambda calculus, nothing else. What do they need? At first, how can they define such a function? In lambda calculus, everything is terms. So this means that we define it as a term, and this function receives only one argument. This means that they can define it as some lambda function which takes some number, and let's do some binding for some naming for this term. I will name it as a fuck. After they have this number, what we need to do? Actually, our definition depends on what n is. If n is 0, we can return 1 and define the function as a 1. But otherwise, we need to take this number and multiply it to again to factorial function with the n minus 1. Let's write this. So first check we do for is 0. I will use alias here. Of course, it's just an alias to some lambda term, and I will provide all these lambda terms later in the end of the video. But for start, let's write it just as an alias. So is 0. The check for 0 our number n, and if it is 0, we provide 1. Okay, and how we provide 1? So we take this boolean value and put it into the if term, and I also provide it later. It's just a lambda term. So we put it into this if term, and if it is true, then they want to reduce it to 1. And if it is not, we want to reduce it to something else, and this is the multiplication term, which I provide in the end of the video. And this multiplication term, actually what they multiply? They multiply this n with some term, and here we want to take the factorial again and provide and apply it to a predecessor of n. Okay, but we can do this because they have this fuck here, which is actually somehow some self-reference to this fuck, and we didn't have the recursion in lambda calculus. Actually, we have the better equivalence here. What we can do, they can abstract out this fuck. So I can provide some argument or abstraction here and replace it with this argument and provide some application like this. Okay, now what I have some lambda term which is applicable, and they apply to it some term fuck, and it returns to us the term fuck again. What does it look like? Yes, of course, it looks like a fixed point. We have some function here. We apply to this function some another function, and again we have some function. And well, how can we find this fuck? By using the Y combinator. Yes, so this means that I need to take this, all this thing inside the parentheses. Let's give it some name. Oh, I just give to it some name. Fuck. And save it as it is. Oh, syntax error, of course. What I do wrong? No, I think aliases must be to the uppercase letter. And now it say to me that so it can't provide. It can't compile this because the alias if was not found. So I need to at this moment provide all these aliases. If is 0, mult, and so on. And let's do it. Let's do it. Okay, now I provide all of them that they need, and I'm not going into details why they work, but they work. They do as they expected to do. So here they have predecessor. This is -1 is 0, Y combinator, if, and multiplication, two numbers. And now I just do the alias. Provide the alias for fuck function. Oh, 0, 0. Of course, it's 0. It's 0. And the done. Okay, it accept this fuck. And what we need? Actually, we need some last step. We need to define the actually fuck. Our fuck function, which defined as we need to take our fuck helper and apply it to Y combinator, and it will return to us the fixed point. Actually, this fixed point is a factorial function. Yes, and it looks like this. The one bad thing with this calculator that it is not recognize the aliases inside these definitions. It can be look bad if the author make this recognition here, but anyway, it's okay. It's our factorial function encoded with the lambda calculus. Oh, of course it is look very terrible, but we can try to, at least we can try to run it. Let's run it with a 0. What is the factorial of the 0? And you can see that here we have some better reduction steps, and at the result, here we have the last last term, which actually represents our result, the number 1. And let's do factorial of 1. We have more steps, and now we have 1 again. Okay, let's do 2. Let's do 2 and go to the end. You can see that we have more reductions here. but now we have as a result 2. Okay, now let's go again and try to calculate 3. Okay, 3, and try to, you can see this process became more harder. Oh. Interesting that this calculator implemented in such a way that it doesn't evaluate all the expression. It wait for me until I go to the end of the document, and after that it provides some more bunch of results. And here you can see that they have how many applications? 1, 2, 3, 4, 5, 6, as expected. Our factorial works as expected. Let's make 4. I think it will be long, but okay, let's try. At least I try. Okay, factorial of 4. Go to the end and let's do the computations. Very long process. But let's go. Fuck. This is really fuck. Oh, we finished. And how many we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30, 40, 60, 70, 80, 90, 20, 21, 22, 23, 24, 25. 26. Is it correct result? Factorial of 4. No, we need to have 24, I think. Why count 26? Okay, let's try again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30, 40, 50, 60, 70, 80, 90, 20. 1, 2, 3, 4. Yes, 24. Okay. It is very tedious to read this thing. It will be good if the author of this calculator did add this ability to squeeze some aliases. Okay. But anyway, this is a very simple, interesting calculator. I think it's written in Elm, a very interesting language. Which compiled into JavaScript, and actually this is Haskell inside the browser. Okay. I'm not going to calculate 5. I think it will be very long and very tedious to count to 120.